Students often leave IPLS courses without a solid understanding of fluid dynamics, which is valuable when it comes to success in their future biology courses. In an effort to reconcile this issue, researchers at the University of New England developed a kinesthetic circulatory system model, or KCSM, in order to improve students' understanding of the circulatory system. Our goal was to integrate several fluid dynamics principles into a single model in which students develop understanding of the equation of continuity, Bernoulli's principle, and Hagen-Poiseuille's principle. As you can see, the parameters of the KCSM are that the tubing is transparent so fluid flow can be actively observed, fluid speed is visually detectable by observing air bubbles pumped into the system using a syringe, pressure can be recorded at 9 different positions in the model with pressure sensors, the speed of the bubbles and therefore fluid can be measured using high-speed video recording, the fluid flows through different branches of different cross-sectional areas, changing the fluid speed, demonstrating the equation of continuity. The different fluid speeds impact local pressure changes, demonstrating the Bernoulli principle. The fluid also travels along tubing of different lengths and radii, which impact global pressure changes, demonstrating the Hagen-Poiseuille principle. Actual data from measuring fluid speeds and pressures is presented in the second figure. There were 3 groups of participants. All 3 groups were asked to make predictions on how the speed and pressure of the fluid would vary in the system. Common predictions are shown in the third figure. All students were also pre- and post-tested with a second-generation multiple-choice 12-question survey developed in-house based on common student errors observed by instructors. 5 questions were selected for analysis based on relevance to concepts demonstrated by the KCSM. These questions included a range of conceptual, diagrammatic, and graphical representations of the 3 principles previously mentioned. Group 1 was pre-tested 1 class period before content coverage and post-tested 1 to 2 weeks after. The purpose of this group was to test the effectiveness of the preliminary demonstration on student understanding of the fluid concepts. Group 2 was pre-tested after a brief introduction to fluids in the physics course and during circulatory system coverage in their anatomy and physiology course. The post-test was administered 5.5 weeks after the demonstration. Group 2 data was used to determine whether the KCSM had lasting effects on student understanding. Group 3 students were part of an accelerated summer course. Their pretest involved open-ended questions similar to the multiple-choice assessment used for Groups 1 and 2. Students worked in groups of 2 or 3 to make whiteboard predictions right before viewing the demonstration. The post-test was an open-ended written assessment that consisted of the same questions from the multiple-choice assessment. Group 3 helped to uncover misconceptions and determine the reliability of the assessment for future generations. As shown in the table, the normalized gains suggested that this demonstration was successful overall, but that students still had a limited understanding of the Hagen-Poiseuille principle and real viscous fluids, as demonstrated in the last figure. We have since added a pump and a balloon artery to more accurately represent pressure oscillations due to compliance in the circulatory system. The new demonstration is detailed in the second video.